Right, so in question 7, we're asked to calculate, a bunch of things for a reaction, for this reaction that we're given, and we're asked to calculate the enthalpies and entropies at two different temperatures for this reaction using the information given in the data section of Atkins. And basically I've just saved us the hassle, so I've copied the data section or sections of it here to help us a bit to the right hand side here, so I can use it for quick reference every now and again. Anyway, so we'll get started right away on that. Okay, so I want to recall first, so we'll start with the enthalpy. So let's calculate all our enthalpy values. I think that will be the easiest. Well, we'll just have to start somewhere. So first, calculating values at 298 Kelvin, because we're given the data in this table is actually at 298 Kelvin. So in other words, that is just normal Hess's law, nothing strange to that. So in other words, that is just normal delta R of the reaction is the molar enthalpy at 298 Kelvin. It's the standard reaction, so that is the sum over I of the formation enthalpy at 298 of the products minus that of the reactants. Right, so we can quickly look that up. So if we look at, this is everything is 1 to 1, so we don't really have to worry about anything. So it is carbon monoxide minus water. So carbon monoxide, everything is just, so carbon monoxide is minus 110, water is minus 241, and then hydrogen is 0, carbon dioxide is minus 1393. Now everything is just, of course, moving around because that's how it's going to work. Anyway, so we have here minus 110.53 minus 241.82 minus, of course, and then carbon dioxide is the reactant, so it's minus 393.51. We did a bunch of examples like this, so I'm just not really going to spend too much time on this, and this gives us a value of 41.16 kilojoule per mole. So that's the molar enthalpy at the standard molar enthalpy at 298 Kelvin. So that's one of the first things that we needed to calculate. Right. Oh my goodness, can I just get somewhere to click? Okay. So that's one of the first things that we needed to calculate. In the same way, we can calculate this or that for the entropy. So the standard molar entropy of reaction at 298, right, is going to be the sum over I for the molar entropy values at 298 of the products minus those values of the reactants So we check them out for, so hydrogen, so products are carbon monoxide and water, so that's 197.6 and water 188.83, and that is minus the hydrogen and the carbon dioxide. So let's zoom in here. So that's 191, 197.67 plus 188.83 minus 213.74 minus 130.684. That is equal to 42.08 joule per Kelvin per mole. Okay. So that is the two values at 298 Kelvin. Okay. Now, if we want to heat, so what happens when we heat something? We already looked at, in the previous example, in the previous tutorial question, at question 6, we looked at the definition of heating for entropy. And it was that the molar entropy for heating at a higher temperature, so in other words, the entropy change is equal to Cp, well, I'm just writing a general definition here, Cpm over T dt, right? Or something like that. And similarly, there's one for enthalpy. It's also to do with the heat capacity. It's also Cpm dt. There's just not T at the bottom. Okay, so when we're heating and we want to calculate the change, we can use integrals. But luckily, we were told at the beginning, assume the heat capacities are constant over the temperature range. So in other words, we can take these heat capacities outside the integrals. So just remember again to keep your mind open for when we're calculating a delta and when we're just calculating a normal delta quantity. So delta R, molar enthalpy, standard enthalpy, at 398 Kelvin. Right, that's where we're heading. That is what we're interested in. Yeah, 398 Kelvin is equal to delta RHM at 298 Kelvin plus the integral between 298 Kelvin to 398 Kelvin of delta R Cpm, because remember we're looking at a reaction, so we have the heat capacity of a reaction dt. And similarly for the entropy, we will have 398 Okay, so we first need to calculate the heat capacity for the reaction. So again, we go back to our table, which is this final column, the heat capacities. So we just use this normal equation. So delta R Cpm is equal to the sum over I of Cpm of the products minus the sum over I of Cpm of the reactants equal to 29.14 plus 33.58 minus 37.11 minus 28.824, which gives us minus 3.21 joule per Kelvin per mole. Okay. So we can substitute that in then. Okay, well, then we have that. We can actually just quickly do the integrations as well up top here. So this integration then becomes delta RH M298 plus so if we assume this heat capacity is constant, so then we can take it outside the integral, CPM dt, oh my goodness, the integral of dt. I'm just going to drop that for writing's sake. Let me write it out. 398. In other words, we have delta RH M298 plus delta R CPM delta T. Is this equation, and this one becomes delta RS 298 plus delta RCPM integral 298 to 398 dt over t plus RCPM ln of TF over TI, which in this case is 398 and 298. Okay, so those are two equations and our unknowns. So in other words, you can just plug it in. So delta R HM 398 is equal to this 41.16 times 10 to the power 3 joule per mole, because we just have some values that aren't in kilojoule per mole, plus there's then a minus, because we have a minus 3.21 joule per Kelvin per mole times 100 Kelvin, because that's delta T, which then gives us plus 40.84 kilojoule per mole. Okay, and delta RSM 398 is equal to the value at 298, which was 42.08 joule per Kelvin per mole, minus the 3.21 joule per Kelvin per mole, times the ln of 398 Kelvin divided by 298 Kelvin. And that can give you a value of 41.15 Kelvin. Joule per Kelvin per mole, my word. Alright. And actually you see there's not a big difference in either of these terms or either of these values. And interestingly enough, both of them slightly decreased, which means if you do these reactions at these temperatures, so at the higher temperature, the enthalpy, there's a little bit less heat given off by this reaction at the higher temperature. Interesting. And there's less increase in the disorder at the higher temperature. It's also interesting. For a reaction which is mainly gases. Yeah, mainly gases. Which actually makes sense, because I mean, if it's at high temperature, then it means it's already a very disordered situation. So in other words, there shouldn't be a large increase in the disorder. It's already very disordered. Yeah, just a bit of interpretation that you can make out of it. All right. So, and I mean, of course, at a high temperature, there's already a lot of heat being expelled. So there's not more heat that can be expelled from the system, though there is still heat being expelled. And disorder, there's still increase in the disorder, even though there's already a lot of disorder. So if you increase the temperature a lot more, I mean, you now have a way to calculate that. So just increase the temperature a lot and see at which stage does it sort of become negligible. At which temperature does the entropy, at which stage does the entropy change, is the entropy change 0, for example. You can sort of calculate that. And then you'll see at which temperature does this, is this situation irrelevant? In other words, is there no change in disorder? In other words, you just go from completely disordered to completely disordered. Very interesting way to think about it. Very nice exam question. Anyway, yeah, so that is question 7.